I have decided that the 256K of onboard SRAM, static RAM, on the RP2040 isn't going to be anywhere near sufficient, so I'm going to have to find a way of adding external RAM. Now, the RP2040 doesn't have an external memory data bus as such. It can address external flash memory via a quad SPI interface, but flash isn't really suitable for storing this kind of audio data. It has very slow write speeds and is more a kind of write once, read many kind of memory. So I'm going to have to find an alternative. If you remember, I said the RP2040 has a number of SPI interfaces. That's the serial peripheral interface. And I'm back on Mouser looking at memory chips, and this one looks interesting. It's 64 megabit, and it has a Q-SPI, quad SPI interface, either 1-wire or 4-wire. Comes in a SOP8 package. They've got 13,000 in stock, and they're just over one of our English pounds. So I think this is worth a look. I'll just do some sums to see what those 64 megabits look like. So 8, 16, 32, 64, that's 64 megabits. There are 8 bits per byte, so that's 8 million 8-bit bytes. We've got 4 bytes per 32-bit sample, so that's 2 million of those, and then we've got left-right samples because we're in stereo, so we can store just over 1 million left-right sample pairs. And as we're running at a sample rate of 48 kilohertz, divide that by 48,000 means we can store around 21 seconds worth of stereo data for just over one of our English pounds. I think that's pretty good. Looking at the pinout of the 6404, it's pretty simple, 8-pin package. We've got plus 3.3 volts ground. Chip enabled, the slash means it's active low. The SPI serial clock, and then the only other 2 connections for SPI are a transmit data, so that's transmit from the host will go into the serial in, and receive data which will come out of the serial out, and the other 2 pins are for 4-wire SPI operation, which we're not going to use. So here we are. I'm just going to use these pins down here. SPI interface, pretty straightforward. So we've got SPI TX, the transmit goes to the receive on the AP6404. SPI serial clock, SPI chip select, as I said, that's active low, and SPI received data, so that's coming from the APS6404. And on some breadboard, it looks a bit like this. I'm taking a 3.3 volts from here, I'm taking a ground from in there, and the other 4 connections are exactly as per that drawing I just showed. The 6404 SPI implementation is all covered in the data sheet, but essentially what you do is you send it a code that tells the chip what you want to do. You then send 24 bits of address data, and then you either send it data to write to the device, or you then read back data from the device. In my code, I've defined the constants for reading and writing. There are some other ones which I'm probably not going to use. I've then also defined the GPIO pins for the various SPI lines, and these are GPIO pins rather than physical pins. Then in main, I'm setting up the chip select line. It's an output, and if you recall, it's active low, so I'm setting it high, so the chip's initially inactive. Then I'm instantiating a SPI object. I'm setting the SPI bus speed to 33 megahertz, and then the SPI format, I've derived this from the data sheet, so the number of bits per transfer, the polarity, the phase, and whether it's most significant bit first or least significant. And then I'm initializing the SPI port. The data sheet tells you all you really need to know about the command sequence. We've got this is for write operations. We've got the write command, which is hex 02, followed by a 24-bit address, and note that it's most significant bit first, and then data, 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 and so on. I've written a little function here that I've called poke32, and this is going to write a 32-bit signed integer into the address that we pass. And as we saw from the data sheet, it needs to be passed a buffer, and this is 8 bytes long, and it starts with the write command, and that's followed by 24 bits of address data, most significant bit first, and then it's followed by the actual data that we want to write. And I could really write these in any order I felt like, provided that when I read them back, I'm reading them back in the same way and reconstructing the 32-bit word that I write in. And so to execute the command, pull the chip select low, write blocking, passing it the SPI object and the address of the write buffer and how many bytes to write, and then afterwards set the chip select high. For SPI read, what's happening, this is serial in to the chip, so you've got the read command, which is hex 03, followed by the 24-bit address, and then the chip replies on the serial outline with the data, however much you've asked for. This is my matching read command, which I've called peak32, and this is going to return my 32-bit signed integer. And again, as we saw in the data sheet, the way this works is you just pass in a simple 4-byte buffer which just says I would like to read, and this is the address, most significant bit first, and you execute the write blocking command, sending that in, and then you execute the read blocking command, passing in the address of the read buffer. And I've just got a 4-byte read buffer, and I'm telling it it's 4 bytes long. And then I'm reconstructing my 32-bit signed integer by just bit shifting the 4 bytes that I get back from the read. And as I mentioned with the poke32 function, I could really do these in any order. I'm just reading unsigned 8-bit data out of the device.